Alright, AP Physics 1, we just finished our last unit on forces and Newton's laws, so now we're going to take a step forward and start talking about circular motion and field forces. So really what we're talking about here is, previously we've discussed how objects accelerate when they're speeding up and slowing down, but what happens when they turn? That's going to be really what we're talking about with circular motion. And when we get to field forces, we're going to start looking in a lot of detail at forces that don't involve contact. So that really is going to focus on the gravitational force and the electric force. But today, we're going to start off by talking about uniform circular motion. So what exactly is that? What are we talking about here? We can probably guess it's going to involve things that move in circles. But there are two ways an object can move, we could say, circularly. One, an object can, spin. It can undergo what we call rotation. So this occurs when objects move around what we call an internal axis of rotation. So if I spin in place here, there is an internal axis of rotation through my body that my whole body is going around. But there's another way we can move circularly, which is through something known as revolution. So rather than spinning, this is when an object will orbit around an external axis of rotation. So there's some point, some line outside the object that it is going around that must be external to it. Now, a couple things about this. First off, when we're talking about rotation, we're not going to focus on that now. That's actually going to be the entire focus of Unit 7. It's literally called rotational motion, which we're going to focus on in the spring. So right now, we're really only talking about revolution, when objects move in circles around some central point outside of them. Additionally, because we're talking about uniform circular motion, what do we mean by uniform? Well, uniform means that things have to be the same. They have to be standard. And what that means is we're only going to be looking at situations that have a constant radius, so r is going to be constant, and we're only going to look at situations that have a constant speed. Now notice I labeled this v here, and we'll get to that in a second, but all the objects we're looking at in this unit will be moving in a perfect circle, so r will be the same, and they're not going to speed up or slow down. They're going to consistently turn, but they're not going to ever speed up or slow down. And we're going to take a little bit of a tangent here for a second and mention the fact that uniform circular motion is a form of something called periodic motion. Now, what is periodic motion? Well, periodic really means kind of repeating. That's motion that repeats itself in these regular time intervals. It's not going to speed up, not going to slow down. It's going to go at a constant repeating rate. And all of these types of motion have two defining characteristics. The first is something called the period. And the period we abbreviate with a capital T, which might seem bizarre, but the period is the amount of time needed for an object to complete one cycle in this periodic motion, which for circular motion means the amount of time needed to complete one revolution, one circle. So the unit is going to be seconds, and that is why it is a capital T, because it is time. But specifically time for a single cycle, not just time in general. The other defining characteristic is known as frequency, which we abbreviate with a little f, lowercase f, which is the number of cycles per unit time. Or in other words, the number of circles per unit time. Now for us, we're really only going to look at the unit of time of seconds. So really what we're talking about here is the number of circles per second. Now one thing we want to highlight here though is that these two characteristics are inverses of each other. So the period is 1 over the frequency is 1 over the period. And you can see that in the units. The period has units of seconds, the frequency has units of 1 over seconds, which can also be labeled as seconds to the -1. So let's go ahead and give an example of just what exactly we mean by this. So let's say I have a ball on like a string, and I swing it above my head, and it completes 4 revolutions, 4 circles, in 6 seconds. And we want to figure out what is the period of this motion and what is the frequency of this motion. Well, we need to be super, super careful because it's really, really easy to mix the two up. Really focus on the units. That will help you think about it. Because for instance, let's say, okay, I've got 4 revolutions in 6 seconds. Well, so let's divide 4 revolutions by 6 seconds. But if I do that, I'm going to end up with 4 over 6, 0.67, and my units are going to be 1 over seconds. Now, you might be wondering why this revolution went. The revolution is just a count. It's just like 1, 2, 3, 4. So we don't need to worry about that. So it's going to be 1 over seconds. But we know this must be the frequency, because this is telling me that ultimately what's happening is that 0.67 circles, so 2/3 of a circle, happen every second. Now, if I want to find the period, I just find the inverse of this. So I take the inverse, and I get 1 over the frequency, which is 1 over 0.67, and I get 1.5 seconds. That the amount of time per circle is 1.5 seconds. So be very, very careful. Just focus on the units. So now let's really focus on some things we might want to know about an object moving in a circle. Like, first off, how fast does an object move in a circle? How can we determine that number? So let's go ahead and draw a circle here, and let's say that this object is moving around the circle, and this circle's radius is lowercase r, which we're going to use pretty frequently, and it's moving in that's a clockwise pattern. And we know it's going to be a constant speed because it's uniform circular motion, but it's not technically constant velocity because the direction is always changing. However, if I want to know the instantaneous velocity, I can do that. I can find its magnitude by really just finding the instantaneous speed. We can then focus on the direction more in a second. But the instantaneous velocity, instantaneous speed, they should have the same magnitude. Now remember, instantaneous just means the velocity at every little instant in time. So if I want to find that, well, I could find the distance that this object goes through and divide it by the time it takes to do that. Well, what is the distance going to be? Well, that's going to be the circumference of this circle. And the time is simply going to be the period, the amount of time for one circle. So I then plug in some equations. I'm going to get V is equal to 2 pi r over capital T, the period, where the period is in seconds, r is the radius in meters, and we're going to talk about what V means in just a second. But this is how fast the object will be moving. I could calculate it with this equation here. But something important to focus on is that the direction of the velocity is always going to be tangent to the circle. So every single moment here, like at this moment right here at the top, instantaneously it is moving to the right. When it gets here, it's going to be instantaneously moving this way. Here, instantaneously moving that way. Here, instantaneously moving that way. Here, instantaneously moving to the bottom left. Here, instantaneously moving to the upper left. So every point, the direction is different, but it's always tangent to the circle. So we want to be careful that oftentimes this is called a velocity. Technically speaking, that is correct because it's instantaneous, but we just need to be careful because really we're calculating it using an equation for speed. But it is something that we call the tangential velocity, just meaning it moves tangent to the circle, the units being meters per second. I've also seen this called the linear velocity. I've seen it called the instantaneous velocity. I've seen it called the linear speed, instantaneous speed, tangential speed. There's a lot of many different names for it, but ultimately all it is saying at every moment, how fast is it moving? We can find by 2 pi r over the period. And additionally, what's its direction? Always tangent to the circle. Well, now that we talked about this object's velocity, well, how exactly is it accelerating? How does that object moving in a circle accelerate? Well, we know for a fact it has to be accelerating because it's constantly changing its direction. It's not speeding up or slowing down, but it's constantly turning. Additionally, if there's an acceleration, there has to be a net force. But what direction does that net force go in? Is it going in the same direction as the object? Is it going out of the circle, into the circle? That's not really obvious. Your first instinct is probably that the force should be out of the circle. Because if you've ever moved in a circle, you feel pushed outwards. For instance, if you're in your car or you're in your friend's car and they're driving and they take a turn, you feel pushed outward to the outside of the car. Similarly, we have this carnival ride here. This is often called like a zero gravity ride or something like that. It's not really zero gravity. But the point being that how you ride in is you get put against the wall and it starts to spin and you feel yourself pushed outward against it, trapped against that wall. And so you might be thinking, obviously, if I'm going in a circle, the force is out. And it's understandable why you'd think that, but it's wrong. This is something actually known as the centrifugal effect. So what exactly is the centrifugal, that's how you pronounce it, centrifugal or centrifugal effect? Well, what it means is that word centrifugal means center fleeing. So essentially outward from the center of the circle. And this is really just a result of your inertia. that when our body is turned, like in a car or on this ride, our body wants to keep moving in a straight line. So for instance, if I have this object here going this way, it wants to move this way, and as things start to turn this direction, it wants to keep going this way, and it's going to appear, and it's going to feel as if it's being pushed outward. So this is simply inertia. And so in other words, the centrifugal effect is really what we sometimes call a pseudo force that seems to push you outward while you're moving in a circle, but that's really just a result of your inertia resisting the true force, which is actually going to be the opposite way. In fact, the net force on an object moving in a circle is toward the center of the circle, which makes sense because you would need to be accelerating towards the center. If I have this object going to the right here and I want to move it in a circle, I have to change its velocity that way. It means I need to be applying a force that way to get it to turn. So this is something known as the centripetal force, which we abbreviate F(c). Now this is the net force that causes an object to move in a circle. And it is always, I cannot star this or circle this enough, always pointed toward the center of the circle. So it may not even be the entire net force, but it's always going to be the net force that is specifically pointing towards the center. And centripetal, because that's a new word for many of you probably, means center-seeking or center-loving. So we want to make sure we get these words straight. Centrifugal, center-fleeing, centripetal, the one we want, center-seeking, center-loving, always points towards the center of the circle. Now we want to be careful that I abbreviated that F(c), but centripetal is not a type of force. It's rather just an adjective we use to describe the net force of an object moving in a circle. So many types of forces can be centripetal forces as long as the objects they're acting on are moving in a circle. So let's look at some examples. So first off, let's talk about the gravitational force. Well, if you've ever looked at, for instance, any sort of picture of orbits, like the moon orbits the Earth in a fairly circular orbit, and in doing so, the net force on it is towards the center. That is the gravitational force pulling it in towards the Earth. That is also the centripetal force because it is moving in a circle. Let's do one that's a little less out there, which is, let's look at this female athlete here doing what's called a hammer throw. So she spins in a circle with that ball on like a chain, and that is causing that ball to move in a circle. That would be a centripetal force pulling it towards her, and that would be the tension force pulling it towards her as she spins in a circle. If we look at the next one, let's say friction. Well, friction could be, for instance, this perfect situation of a car taking a turn. That when this car turns, the tires are pushing it toward the center of the circular arc, and that would be a force of friction, but also a centripetal force. What about normal force? We actually talked about that a second ago with like that zero gravity, right? That would be a normal force pushing you towards the center, but also applies to, for instance, a roller coaster. When you go up and around, when you go up to this point here, the normal force is pushing you in constantly towards the center from this track. If it wasn't, you just fly outward. So that normal force is pushing you towards the center of the circle. That is a centripetal force. We can even have combinations. So for instance, this turn here is a flat turn, an unbanked turn. It's just a flat surface. But if we have something like NASCAR, for instance, has what are known as banked turns. It actually allows them to go around these curves faster. So essentially what happens is that the curve is at a tilt. And that means not only do they have the friction of the tires pointing into the center, but they actually have normal force from the ground pushing them towards the center as well. Now, one note I really want to make real quick is that because centripetal is not a force type, you shouldn't be labeling it on an FPD. You can identify other types of forces as centripetal forces, but it should not be its own isolated arrow on a free body diagram. So let's go back to this question. How does an object moving in a circle accelerate? Now, we already know that the direction must be towards the center because the net force is towards the center, and we know for a fact that objects always accelerate in the direction of the net force, which is Newton's second law. So instead of having the acceleration is equal to the net force over m, now it is the centripetal acceleration is equal to the centripetal force over m. And it's always going to be pointed toward the center of the circle. Now, how can we calculate that? Well, I'm going to go ahead and apologize in advance. I'm just going to give you the equation for the centripetal acceleration right now, and we're going to go over the proof for it in class. The proof takes quite a few steps, and I don't really want to spend a whole lot of time of this video on this, particularly because it's never a proof I'm going to ask you to redo. But I want you to see where this equation comes from. So we will talk about that in class, but the equation for centripetal acceleration is this. AC, the centripetal acceleration in meters per second squared, is equal to v squared over r, where that v is that tangential, that instantaneous velocity in meters per second, and r is the radius in meters. So once again, if you look at that and go, where did that come from? Don't worry, we're going to talk about it in class. But now that we have the centripetal acceleration, we can more formally make an equation for the centripetal force. The centripetal force is just the mass times the centripetal acceleration, so therefore it will be equal to mv squared over r. So let's look at an example altogether of how we can use all the information we started to learn today into one big problem. Let's say we have a person, they're swinging a ball in a vertical circle. So by that I mean they're swinging it in front of them, so it's going up and around vertically in front of them. This ball has a mass of 0.1 kilograms, swung in a vertical circle such that it completes one revolution, one circle, every 0.5 seconds. What is the tension in the string at these four specified points? 1, 2, 3, and 4. 1 being above, 2 to the right, 3 below, 4 to the left. So let's start going through this. First, let's identify some things we know and start calculating some things we can do real quick. Well, automatically, we know that the mass is 0.1 kilograms, the radius is 0.6 meters. If you didn't see that, I wrote that over here. And the period is 0.5 seconds. So I can instantaneously find this tangential velocity by just using the equation v is equal to 2 pi r over the period. Stick in the numbers, 2 pi times 0.6 meters over 0.5 seconds. Stick that in your calculator, and get about 7.54 meters per second. Let's take this a step further. What would the centripetal acceleration and centripetal force be? Well, we can once again stick numbers in equations. The centripetal acceleration is v squared over r, so I take that velocity I just found, square it, divide by 0.6 meters, and we get 12.57 meters per second squared. And to find the centripetal force, we just multiply the centripetal acceleration by the mass of the ball and get 1.26 newtons. Okay, that's all well and good. But this is really the important point here. That because this is uniform circular motion, remember that means r is not changing and v is not changing. So what that tells me is that all three of these values, the tangential velocity, the centripetal acceleration, and the centripetal force, they're going to be constant the entire time the ball is moving in a circle. And that's going to make my life a lot easier. Because now I can start looking at all of these different points around the circle and think about what is the net force towards the center, because that would be the centripetal force. So first, let's go ahead and draw some FBDs for the ball at these 4 points in the circle. Now remember, what we're trying to do is we're trying to find the tension force. And we're going to do that by comparing tension, gravity, and the centripetal force at all 4 of these points. So point 1, when the ball is at the top, gravity is definitely pulling the ball down, and the string tension is pulling the ball down as well, towards the center of the circle. When it's at point 2, gravity is once again pointed down, but tension is pointed towards the center. At point 3, gravity is pointed down, but tension is pointed up towards the center. Now, a couple things here. I know for a fact this one has to be bigger, because for it to move in a circle, it must continually accelerate toward the center. And then lastly, at point 4, gravity is down, tension is toward the center. So I have these 4 different FBDs here. And let's start talking about, okay, well, how does the centripetal force work in all these? Well, in positions 2 and 4, it's real simple. That the only force pointed toward the center is tension, so tension will be equal to the centripetal force. Nice and simple. But for points 1 and 3, we have a combination of things. At point 1, both gravity and tension are pointed towards the center, so they are going to add together. And at point 3, tension and gravity are, well, tension is towards the center, gravity is away from the center. But once again, they're going to have to combine to form this net force, this centripetal force. So let's go ahead and write out for all 4 of these, just the equations I just found. And once again, for points 2 and 4, we already found that the centripetal force on the previous page. We found it was 1.26 newtons. So at point 2, the tension is going to equal that. It's 1.26 newtons to the left. For point 4, it's going to be 1.26 newtons to the right. Both of those towards the center. Now, how can we find the other two? Well, we know that the gravitational force on the ball is 1 newton, because its mass was 0.1 kilograms, so 0.1 times 10 meters per second squared, 1 newton. But how can I find the tension at point 1 and at point 3. Well, I know Fc, the centripetal force, I know Fg, so I should be able to figure out Ft. Let's first look at point 1. Well, the centripetal force is towards the center, and at point 1 that would be down, so it is 1.26 newtons down. Gravity is 1 newton down, so what does tension have to be? Well, 0.26 newtons down, toward the center. And similarly, if I look at the other one, the centripetal force at point 3 is up, towards the center, so it would be 1.26 newtons up. The gravitational force is 1 newton down. So what would tension have to be? Well, not only does it have to be 1.26 up, but it has to overcome that 1 newton down, so it's actually going to be 2.26 newtons up. And let's look at something here that's a little interesting. That the tension is not constant as we spin this in a circle at a constant speed. But that makes sense, because at the bottom we're having to fight gravity to pull it in a circle, and at the top gravity is helping us pull it in a circle. So it's real hard to move it around at the bottom, should be nice and easy at the top. So this was a very dense video on uniform circular motion. So we want to make sure we can do a few things here. One, can we describe the parameters of uniform circular motion? In other words, that it's constant radius, constant speed. We're talking about revolution, not rotation. Can we determine the magnitude and direction of the tangential velocity, centripetal acceleration, and centripetal force on an object moving in a circle using the equations we've just learned? And knowing that tangential velocity is always tangent, the other two are always pointed toward the center of the circle. Can we explain how the centrifugal effect takes place? Why is it that we feel pushed outwards when really the force is towards the center? And can we analyze scenarios involving circular motion by setting the centripetal force as the net force towards the center of the circle? And keeping in mind that it shouldn't change if we're in uniform circular motion, by using that we can figure out, okay, what are some other things we might want to know?